basic introduction of computational chemistry course, where focus was made on three aspects: theory background, practical skills to do computational characterization of materials, and scientific communications when the results of simulations are compared to experiment or to another theory or to consistency of the logical consistency of the result. So in addition to lectures, which are pink here, and labs, which are green here, there were individual research projects that class attendees were selecting subjects themselves, and this mini research project will be delivered today. So the subjects of this mini research projects will be very broad. I will briefly announce what they are, and the plan for presentations is as follows. Each presenter is making the best effort to present within 5 minutes. I understand it is a big challenge, and then the floor is open for questions. So if questions will be asked longer for 5 minutes, I will encourage to keep going. Under 5 minutes, it is very welcomed. If you're not sure about a question or you feel that you can forget, just type it in the chat line. And questions are encouraged both from class attendees and from the visitors. So the class contained 4 chapters: molecular modeling, basics of Hartree-Fock theory, basics of density functional theory, and excited state theories such as density functional theory. And the presentations here, there will be 6 mini research projects. So speakers, please notice your order. So Boston, Keya, Sarah, Lina, Lola, and Steven. And with this, I would like to invite Boston Heaford to join the stage, start sharing, and 5 minutes are yours.
All right, so just double check, is it sharing the screen, and is it sharing the right one, the actual presentation, not the...
It does.
Okay, good. Alrighty, so I did my project on the characterization of bismuth telluride, and bismuth telluride is a material with many interesting and useful properties. In particular, it's a very well-known thermoelectric used in many applications. Just one common one is in refrigeration. There's also ongoing research into using bismuth telluride in areas such as power generation. And one area that in particular interests me is solar power. And this study attempts to computationally characterize two-dimensional bismuth telluride to help set the foundation for future research into the material and its applications. So just a little bit of background on the methodology and computational details. The characterization was performed using VAS, the Vienna ab initio simulation package, using density functional theory. And density functional theory essentially is solving Cohen-Sham equations, which is that first equation that I have listed there, to determine the total charge density, which is then used to determine the potential. And I skipped a few steps between those just because time and slide space, but I have the equations at the end if anyone's interested in seeing the whole walkthrough. So a little bit more details on just the computation. I use the projector augmented wave method to treat the interactions. The total energy calculations were performed using the Purdue Burke Ernzerhof generalized gradient approximation. There was a gamma-centered K-point mesh of 25, 25 by 1 to sample the Brillouin zone. Cutoff energy of 220 electron volts, and the structure was relaxed until the change in total free energy between ionic steps was less than 1 times 10 to the negative 6 electron volts, and the energy cutoff criteria was 1 times 10 to the negative 7 electron volts. So after the relaxation, these were the structures that I got. No, the first image is a image of the structure relaxed at 0 Kelvin, and the second image is the structure. It's a snapshot of the molecular dynamics run at around 300 Kelvin, or at 300 Kelvin. And in that run, there's very little motion observed in the system because it's at a relatively low temp, and all of the constituent atoms are relatively heavy, so they don't move around that much, and it's a stable configuration. I have a video of the run here. I won't play the full thing because it's about a minute long and only have 5 minutes for the presentation. But as you can see, not much happens. It's stable and, again, low temperature, so it's not going to break apart or anything. But and so I'll just leave it at that and move on. Also, if you saw the atoms blinking in and out, and that's because one atom is moving over out of the unit cell, and then another atom is replacing its position. So they pop in and out as far as the visualization is concerned, but they're still there. And so after I did the molecular dynamics run and the relaxation, I moved on to do the momentum dispersion, which is just taking the HOMO and LUMO orbitals and plotting their energy at each individual K point coordinate. And that gives you this picture of the momentum dispersion. And that lets you see like the gap between the HOMO and LUMO. And as you can see from these plots, the gap is centered at the gamma point, the 0, 0 for Ky and Kx. And that means it's a direct band gap system. And between the anions, cations, singlet, doublet, and triplet, the structure doesn't really change much. The bands just kind of move up or down a little bit depending on the system, but the overall structure remains consistent. The density of state plots here as well shows you how again, anion, cation, +2 anion and -2 cation. Excuse me, backwards. But and then just singlet, doublet, and triplet for the neutral system. And the density of state shows that the band gap is approximately 0.51 electron volts, and we know it's a direct band gap as well from the momentum dispersion previously. And then finally, we have the oscillator strength, which is essentially showing you the absorption spectra. It's the strength of, or the relative probability of the material to absorb light at a specific wavelength shown here. And as you can see here, there are a few different spikes in the absorption spectra around 1 to 1.1 electron volts, and then 1.3 to 1.4 electron volts. There's some pretty strong absorption, which are both in the infrared range, which is to be expected for bismuth telluride. And so for conclusions, the optical and electronic properties of bismuth telluride have been characterized, and from the simulations it can be seen that the material has a gamma point centered direct band gap, approximately 0.51 electron volts, and absorbs strongly in the infrared region of the electromagnetic spectrum. And these results, along with others I didn't have time to discuss, are the first to help further future computational research into bismuth telluride. And thank you. And does anyone have any questions?
Okay, please join me thanking Boston for intense and interesting presentation, and paper is open for discussion. I will ask the first question, but more questions are welcome. So, Boston, would you please go to the slide with the model and with image of the model?
This one?
Yep, and explain a little bit more why some authors call it two-dimensional material, and two-dimensional in which directions? Like, what are the axes here?
Yep.
And why did you explore momentum dispersion in X and Y and not in Z? So please please tell more about it.
Yeah, so bismuth telluride, in the axis that I have shown here, the z-axis is up and down. That is the that's the axis where I only had the one point in the K-point mesh, and the plane is the XY plane, where it's 2D, and it's considered 2D material because of van der Waals separations between each layer of bismuth telluride, kind of similar to graphene, if I'm not mistaken. My understanding of that is still relatively limited. I'm doing my best to learn, but that is, to the best of my knowledge, what's happening there. And did that answer your question fully, or was there anything else that I skipped?
Yeah, it answered first part, but the second one, can you please show your momentum dispersion?
Yep.
Which is it is quite an achievement to. So it's let me make a comment. Unlike standard approach in community where one explores momentum dispersion along high symmetry points, Boston is doing full scan of all values of momentum in X and Y direction. And it looks like he's showing top of the valence and bottom of the conduction bands. But there is a scan along X and Y. Why you are not showing scan along Z? What would you expect?
Yeah, I have, I think, a slide for that. Let me skip way forward in my, I think I had a slide for it. Oh, no, hold on.
You can tell just by words.
Yeah, okay. So again, my understanding of it isn't that strong, but it shouldn't really change too much between or in the Z direction of the material.
Oh, you're telling me it will be flat.
Yes. And again, my understanding as to why that would be is relatively limited at the moment. That's something I still need to look into.
Let me provoke you. Would you agree that in Z direction it will be more insulating and X and Y it will be more conducting?
Yes. Yeah.
Okay. More questions from...
May I?
Yeah, please.
Okay. So Boston, the first one is more like a comment.
Mm-hmm.
Yeah, two important effects, in this material. One is, the first is spin orbit interaction. Both bismuth and telluride are heavy elements, so that's where bismuth telluride has very strong orbit interaction. So if you include that effect, the electronic structure and the optical properties may be significantly different. That's the first thing. The second thing, you also mentioned that there may be van der Waals interaction between the layers. So if you include that, you also see changes in the electronic structure, and I don't know how much it's going to change. Okay, that's my comment. Now the question is, I saw that you did some MD simulation.
Mm-hmm.
What is the purpose of the simulation? Because I thought that you are doing static calculations.
Yeah. So I want to do a lot of different things with the material. I was limited by time to get some of these things done, but I wanted to study the material at different temperatures as well. I only got around to doing a 300 Kelvin one. I want to, the static properties were the ones that I was most interested in, which is why I stuck to those more than the molecular dynamics run. But in the future, I want to do more molecular dynamics run and see how those affect the system at all. Including other properties that I haven't had time to talk about or haven't even had time to go into research yet. But I mostly just included it because it was done and it was relatively interesting. But again, the static properties, as you pointed out, were the ones that were more focused on and was kind of the primary area of the research that I've done so far.
Yeah.
That answer your question, hopefully?
Yeah. Thank you.
And no more questions. Last question on the account of exam for computational chemistry. What is self-consistency in Artifoco in DFT? And if you have some illustrations, you can show.
Yeah. So this is kind of a general flow chart for the algorithm or the self-consistent process that VASP and other, I'm sure other DFT programs use. Basically, you start with some initial conditions, and then it starts running through these equations and updating the total energies, and it keeps looping through these until the total energy between individual steps is less than some energy cutoff value that you set. And that should mean that you're at the minimum, the ground state energy, which is what you're generally trying to get to in these calculations. And so that's, you're self-consistent with itself. It just loops through and compares new values that it's calculated to the old values, and it keeps trying to get to the lowest potential that it can, which is the low, and it calculates that through the density functionals. So to the best.
No, that's great. That's great. Yeah, thank you. If there are no more questions, please join me in thanking Boston once again. And Boston, you can stop sharing. The next presenter is Kamrun, Nahar, Keya, and please start telling your story, and I will assist in flipping slides.
Okay. Thank you, Professor, for sharing the slide. So I'm doing in this project on the computational simulation of the undoped and P and N-type doped the Cis-polyacetylene using density of state and absorption spectrum. Next slide. Okay. So the objective of this project.
Just a second.
So the objective of this project is actually to understand the charge transfer because here we use two-type dopants, and we want to see what happened when we use this one. And those dopant actually control the conductivity. So we are checking those things, and we also prove that the doping and we inject the charge, they actually give the result, and those results are more or less same. Next. So here we want to explain that the conductivity, electrical conductivity. So electrical conductivity actually the property of the material which determines how well the conductivity, it shows the conductivity. So in the first, the right side, and we are able to see the general form of the material, that how it looks if the band gap between the conduction band and valence band is more, it's that material behaves like an insulator, and if less than the insulator, then it behaves like a semiconductor, and if the conduction band and valence band, they are overlap with each other, it's behave like a metal. And in the right side there is another figure. So it's actually shows our project, that how it goes on. And there in the first, that one in a neutral state, it shows that in a semiconductor state, this valence valence band is occupied, and the conduction band is unoccupied, and this one is in a semiconductor phase, because there is band gap. We are able to see the band gap. When we remove some electron from the conduction band, then we are able to see that the LUMO is near to the valence band, and so they are overlap with each other. So it now behaves like a conductive material. Then if we add some electron inside the polymer in polyacetylene, here we use polyacetylene, then their HOMO is go up, and it's overlap with the LUMO, so its behavior, it's like shows the conductivity of the material. Next slide. Okay, so for this project, we actually use three model of the polyacetylene, cis-polyacetylene we used, and first one is the undoped material, undoped one, and there we then inject any dopant. In the B, figure B, one B, in there we inject P-type dopant, and P-type dopant actually is like they accept the electron, and p-type and in figure A 1C, here we used added two type dopant, P and N. So P actually p-type dopant is an acceptor element, and N-type is a donor element. So there in the p-type and dopant, there there is a sodium. It's a blue. There is a sodium ion. So it's easily can share the electron to the fluorine, and fluorine and we are able to see the this one that fluorine can easily take that electron from the sodium. So why we use this type of dopant? That because we want to prove that using dopant the conductivity of the material will be increased. Next slide. Okay, so here we did density of state graph, shows density of the state graph for the undoped, doped, and the co-doped model. So first, and the neutral first, that the first panel, A neutral, B cation, and C is anionic state. So from the figure we are able to see that there is a peak that occupied orbital, that one is 0.4, and the unoccupied is peak is 0.8. So there is a band gap. It's visible band gap. But if here from the figure 1B, we are able to see that the occupied and unoccupied, they are actually overlap with each other. So it behaves, it shows that that when we remove electron from the model, it behaves like a conductive material. So same thing happened with the anionic state, but if we see all the figure, only we are able to see that the this figure, like 1B, that one actually show more conductivity. I want to show you on the table. Professor, just could you please click that? Yeah, so there we are able to see from this table, we are able to get a conclusion that when we did anionic and cationic calculation, and then the undoped model in a cationic state, that one show more conductivity than others. Professor, yeah. Okay, it's okay. So this one actually we are showing the absorption spectrum analysis, and W is the frequency at a zero state. So Here we are able to see that we already proved that band gap in a cationic state is less band gap means more conductivity, and when we indeed in the absorption spectrum, it also shows that at zero energy it shows more absorption. Next slide. Okay. And so from this one, we are able to get that the cationic state and the undoped cationic state compared to the other model, it shows more absorption at when wavelength is more. It's like reverse to the absorption spectrum. Next slide. Okay. Now this one we are showing the charge density of the undoped model, and here we actually showed two type position X and Z, and in the X position we are able to see the peak, and that peak actually because of the electron particle of the electron we are able to see from this box, and there that peak means in that stage that blue cloud shows more charge density, and there in the Z position we are able to see that there is a high peak. That means there is this one shows more charge density, and this the third oligomer and the second oligomer there is orbital. They actually almost overlap with each other, so that's why this stage actually shows the conductivity, proves the conductivity of the result. And similarly in the homo orbital, we are able to see that at the edge in the X position, at the edge of the box there, it shows more charge density. Next slide. Similarly, these things happen that a high peak. High peak means it shows the more charge density, and it's happened in it shows the third oligomer, and in the LUMO plus one it shows more charge density at the edge of the box. And I want to explain the doped one. What's the next slide? Next slide. Okay, so because in this model we used the dopant here, so for the dopant we are able to see that and where that this doping is added in the oligomer, there is no charge density. We are it's visible from this graph. So we are getting this conclusion that this doping actually affect the charge intensity, and we are able to see that the charge density almost shift on the other oligomer, and in the middle position it shows the more charge density. Next slide.
Okay, let me suggest to wrap up and go to conclusions, because we are
just go to the MD simulation and then conclusion. MD DOS. Okay, and so after that we did MD. Professor, could you please show the DOS graph of the Okay, so after that we did heating and MD simulation. Actually, from the MD simulation, we are getting that after doing this one, the band gap decrease a lot. So all of them, it's a neutral state. There is no removing or no adding electron, but it behaves like a conductive material. And then conclusion. Okay, so after that we had a conclusion, and that when we compare our result, undoped material
Sorry, just a second. Keep talking.
Okay,
Keep talking.
undoped material actually behave like more conductive material, and we are actually adding doping and injecting charge, and those are control the conductivity of the cis-polyacetylene material, and we are proving that the injecting charge and adding dopant more or less shows the same result. Let's say.
Okay, please join me in thanking Keya. And paper is open for discussion. Keya, since I'm showing your slides, please look if there are something typed in the chat line.
Oh, okay, I'm seeing it. Let me.
Can I have a look at the graph, the slide where you show the density of
there is no
states?
question in the chat box.
Mm-hmm.
Yeah, I think that's one from the started calculations.
This one?
So here is the material a metal or a semiconductor? Because at one point you mentioned that it has a small band gap, about like 0.3 electron volt or so. Yeah. But when I look at the first graph here, like figure 2a, I don't see any band gap in that plot. So can you explain that?
So it's first at a neutral state. There we are able to see few means small band gap.
But I don't see it here in figure 2a. I don't see a band gap here.
Yeah, because I already said that when we add doping, p-doped and n-doped, they actually...
No, Keya, please tell about how do you generate density of states, and tell more about width parameter, how the delta function on the bottom equation is represented.
Professor, actually, this one, we add P in doping there inside.
No. Explain the procedure. Professor Hang is interested how the density of states is calculated and why on the panel A it looks like there is no gap. What is the gap for the panel A according to your calculations?
Panel A 0.3 band gap. Around 0.4.
Okay.
Yeah, but we don't see that. We don't see that.
So
in the
why the purple and white areas overlap? Is it artifact that you can fix, or it is objective observable? How would you learn what is the band gap based on your panel A? Should you look on the area where purple and white overlaps, or should you look at the tops of the peaks?
From the graph, yeah, top of the peak.
So can you explain about the width of these peaks, what it is? And is it results of calculations or human manipulations?
First, what I did in that we have data, so from that I able to get the band gap from the data, and then I am trying to explain that one from the graph, and it's visible that from the peak there is occupied, and the figure 1a, no, sorry, 2a, so it's a peak around 0.4 and there is 0.8. So if we did the difference, then it shows that around 0.4 band gap there. It's visible.
Yes, but to finally convince Professor Huang about the question, when you prepare density of states image, which parameters do you enter, and do you introduce the width corresponding to each orbital energy? What was this width parameter, and can you change it? Say yes.
So Yeah, I follow the step of the density of this step. Then I got this result.
But can you change the width of each peak?
Width of
Width parameter.
yes,
Yes. Okay. Thank you, Professor Hank. Does it satisfy your question, or you need more explanations?
I think that's fine. That's fine. I mean, the main point here is it seems to have a small band gap, but because
Yes.
during the calculation, you know, there is broadening effects. You know, you have to use either a Fermi function or a delta function with a finite width, right? And
Yes.
if you choose the parameter if the parameter is quite large, you know, you had overlap.
Exactly. Exactly. And
it's just the artifact from the calculation.
Exactly, and it makes an deceptive impression on the graph. But objectively, the gap is here. Yeah, thank you for the question. More questions to the speaker?
Okay, here is two questions, one from Amir and one from
okay, please read them.
Lina, I guess.
Please read them.
Okay. First, Amir's question: did you test both charge injection and adding of real dopant? Yes. Yeah. So we add charge and also we add doping as well. P-type and N-type doping inside there. And Professor Kilina's question.
Yeah, just a second. Please indicate which of your panels on the DOS corresponds to real dopant. For example, real P dopant.
Okay, so real P doping is the D, 2D. This one.
Okay, so B is injection, D is dopant. Okay, yeah, thank you. And please read the second question.
How do your calculated gaps agree with experimental values for this material? How do you calculate?
So if you didn't check, say I didn't.
Yeah, I didn't check for the experimental things. It's just a computational part. So if I have chance to check, then I need to do that later because I don't know.
But even if
I don't know, I have no knowledge. Means I need to check in the experimental part. I never did.
But even if you didn't compare directly to the experiment, what do you expect based on the calculations which you are doing? So you're using the functionals, right? And you probably know already what the problems or maybe what the weaknesses of using this or that functional. So what exactly you expect? Are you really expecting that your band gaps would be very accurate, underestimated, overestimated? In general, maybe not just for this material, but some general trends in the functionals. Like if you choose GG, it looks like you were doing it with PBE, GGA functional, right?
Yes.
So what do you know about GGA functionals? Are they really very accurate in providing band gaps for the semiconducting materials?
Or they make the gaps somewhat smaller than they actually are.
Smaller or bigger? What do you know?
Sorry, Professor, can you repeat the
How
question?
the value of the gap depends on the choice of functional. Would the gap become bigger if you use different functional?
Then I need to check with other function because I just use one function and it shows the less band gap. I don't know that if other function will show the different band gap or not. But I think it will be more or less showing the almost same. Little bit difference may be occurred, but not too much.
What if you take other functional? Can you say which functional you can take and what you expect? The gap will be bigger if you take another functional or smaller if you take this other functional? And name the functional which you can take if it's not your PBE. Or you don't need to name the functional, you can just name the type of the functional.
Okay.
So there are GGA functions, there are hybrid functions, there is long-range corrected functions, there is
there is a hybrid function.
GGA
HSE
Okay.
06, that one, we can use that one.
Okay, if you use HSE, then you expect the gap will be smaller or larger comparing to results which you already have.
Gap, and that will be give the more band gap.
Okay, so it will increase the gap, and HSE is called actually short-range corrected functionals. Okay, so the gap really depends on the function which you use, and GGA functions are known to underestimate the band gap for semiconducting materials. So usually they do not agree with experiment. It would be really surprising if they do. So it is known, the common failure of GGA functionals such as PV is that they make the gap smaller comparing to the actual one. And there is a reason, but I probably stop the discussion here. This reason probably will be another question to another student.
Okay, are there more questions to Keya? More questions one, more questions two, more questions three. Let's thank, please join me thanking Keya once again. And the next presenter will be Lina Alhalhooly. And Lina, please consider to share your screen. You should be able, as a co-host.
Okay. Mm-hmm. Okay, so is that okay now? Can I start?
Yes, please.
Okay. Hello, everyone. Thanks for attending our presentation, final presentation today. Today, I'm talking about adsorption of a L-lysine molecule on AU111 surface using the L-lysine carboxylate ion. Before going to the talk, I will just give a little introduction about the gold substrate. So the unique optical and physicochemical properties of gold make it a strong candidate for using as a substrate in the biomolecular research, sorry. And also gold has excellent adsorption mechanics, where gold substrates can be used to immobilize biomolecules effectively. So in this study, we utilize the vast simulation packages to measure and justify a strong binding that we obtained after doing the calculations between the L-lysine and the gold substrate in a certain orientation. So the outline would be talking first about the L-lysine molecule adsorbed to AU surface, which is our model that we use. Then calculations of density of states and partial charge density at two temperatures, 300 Kelvin and 600 Kelvin. Then we calculated binding energy. After that, we have some molecular dynamic simulation for the system after heating to justify our binding energy results. So here I'll start by, in this example, like as important studies were conducted on the biomolecules which can be absorbed to the gold substrates. For example, here the gold substrates was modified with carboxyl terminated monolayers to achieve high affinity for specific peptides. So the findings here revealed, like for example, better immobilization coverage and bioactivity on the gold compared to silicon substrate, which is common used in the biomolecular research. which is, so these findings like are crucial for biosensors efficiency, for example, for this model. Gold substrates are also remarkably useful for biomolecules visualizing, and also, as we said, biosensing and binding spectroscopy research. So thus we investigated the binding between L-lysine molecule and the gold substrate. So the L-lysine here, why we choose L-lysine, this is our model, why we choose L-lysine, because it has a carboxylate functional group, which is supposed to increase the binding affinity. We hypothesize that it increases the binding affinity of the biomolecules on the absorbed to the substrates, and it has also 2 amino acids, which are considered the main components of the peptides and proteins. So this is our model. As you can see here, it's composed of 4 layers of gold and just one molecule of L-lysine, which is positively charged on one of its amino groups and negatively charged on the carboxylated group. So here we started by plotting the density of the states before and after heating the system. The band gap of our system is very, very low. It's overlapping with the conduction band. It's comparing to the partial, as we can see here. And next slide, this is the binding energy calculation. So for the combined system of gold and L-lysine, we get this E1 around minus 314 electron volts. For gold and L-lysine separately, we got these numbers, and then we calculated the binding energy by subtracting E2, E3 from E1 to get around minus 20 electron volts, which is very high. So this is why we try to figure out like why we get that high energy, binding energy. Because of that, like to justify the strong binding energy between the L-lysine molecule and the gold surface, the heated system here we could show like from 1 to 8 snapshots for the molecular dynamic simulation. So the heated system has shown that we can see obviously protonation for the carboxylate ion COO minus, and the protonization for the ammonia NH3 plus. So here comparing the atomic structure, we can before that. So if we compare the atomic structure, it's obviously observed that the temperature, as the temperature increases, the hydrogen ion breaks from the ammonia and binds to the carboxylate group. So here are the videos that for our model first, so we can show that chart density, how it's distributed over the molecule, the atoms in our model. And also the next video is after heating the system. You can see how the hydrogen atoms, like the hydrogen moved from the ammonia to carboxylate group, and because of that, we can say like here we get different situation after heating, why we got another, like the molecule converted from L-lysine, that the one we used before, to lysine molecule with this stable structure. So what we conclude after that, so we concluded like because of the strong binding was verified by heating the system here, and molecular dynamics demonstrated the changes that occurred on the molecule through the heating process. So here comparing before and after adding the energy by heating, the L-lysine was polarized before due to the existence of the carboxylate ion and the ammonia. It was stable, which leads to strong binding with the gold surface. This is what concluded about our situation, but after heating, we noticed that the protonation of the carboxyl ion give us the lysine molecule, which is not polarized, maybe just reduced the binding and also verified the strong binding that we got. So we concluded in summary that the polarization of a lysine molecule because of the heating confirms our hypothesis of a strong binding between our molecule L-lysine with the gold, and that suggested orientation that we applied. This is all about my project, and thanks. Welcome to questions.
Okay, please join me in thanking Lina. And presentation is open for discussion. So just a comment, it looks from your simulations that there is a facilitation of transformation between L-lysine to regular lysine, right?
Yes.
Is regular lysine more stable or without gold, or it is only because of the gold?
So, as from my experimental experience, I know that we could use L-lysine or lysine, depends on what the purpose of using the substrate. For example, here L-lysine, through doing the calculations, I see it's a strongly bind to the gold crystal because of the carboxylate ion. So mostly I see its binding in nature due to the amino acids, which is not really strong. So maybe just getting that orientation and trying to get that bond, which make it really strong. So if it's stable, so I think we could get I'm not sure about how much both of them are stable, which is more stable than other, but I could see we could get both of them and use both of them in our research, depending on the purpose.
Okay, there is a question in the chat line from Professor Helena. So the question is, in the introduction, the figure shows that gold interacts with molecule via sulfur to gold binding rather than carboxyl group. Why did you use carboxylate instead?
Here?
Uh-huh.
So it was bind to the carboxylated group, you said, Doctor?
Yeah, why carboxylate?
Okay. So it was hypothesized in this study that the carboxylated group increase the affinity of binding to other peptides or other proteins if we need to. So it seems like it's making maybe a high negative charge, as we know that the biomolecules mostly have positive charge. So it could increase the affinity and binding with the peptides. I guess that. But this is why we used the L-lysine and trying to study the binding specifically between the carboxylate group with the gold. So here it was the purpose of that study is just because it increases the affinity binding.
Okay, thank you.
So, am I understand correctly? You're not expecting that L-lysine, exactly in a form without any modification, will bind to the surface as strongly as, I guess, any other modification which really allows this sulfur-gold connection, right? So this is known that gold really will provide more strong interaction if you have a group which includes the sulfur to interact with the gold.
Yes, exactly. Yeah, that's exactly what they investigated, because in the labs, mostly in experimental work, we use silicon substrates, maybe because it's cheap or it has also good characteristics for adsorption, the biomolecules. But that study shows like also gold has really future like we can use it as like yes for better characteristics or better features.
Okay, good, thanks.
So more questions to Lina.
May I?
Yes, please.
Yeah, so I had a question about, it's a general question about the calculation. So I still don't know why you had to do MD simulation for this. Of course, if you do MD simulation, you can set the temperature effects in, but usually you can still learn a lot, from just the started calculations, right? At 0K. Because when you do MD simulation and you take, a certain configuration out of the simulation, it can be anything, right? Because it's not a really ground state configuration, right? So can you tell us a little bit about it, why you decided to do MD simulation?
Yes, we first we were thinking about why we got this high binding energy, and then we said maybe to see like after heating the system and doing we could see obviously that what happened. So we could see that this hydrogen ion, how it moves. It wasn't here, but after heating the system, it moves from this ammonia. It was here ammonia, and it moves to bind here. So that we expected that this will decrease the reduce the polarization of the molecule, the L-lysine molecule, which may reduce the binding to the gold.
So that's fine. So here's my suggestion. Let's say that after you do MD simulation and you took maybe 5 or 10 configurations from MD simulation and use them at the initial structure and do just static calculation. At the end of it, look at the configuration and see if there's any different, or look at the lowest energy configuration.
Yeah, that's really good suggestion. You can do that. Thanks, Dr. Han.
Okay, let me check if there are more questions to Lina. More questions 1, more questions 2, more questions 3. Please join me in thanking Lina once again. Lina, you can stop sharing.
Okay, thanks.
And the next presenter is Sarah. So Sarah Ghazanfari. So please share your screen.
Thank you, Dr. Keya.
And it will be continuation of the previous subject in a sense that it will be adsorption of biorelated molecules to surfaces.
Yeah, okay. Hello, everybody. Today I'm going to talk about the interfacial interaction between amino acid and Montmorillonite utilizing density functional theory. For the introduction, I'm going to talk about Montmorillonite and tyrosine and introduce them. For the Montmorillonite, we can say it's a member of a smectite group in the clay mineral, and it consists of one aluminum octahedral sheet sandwiched between 2 silica tetrahedral sheets. And for the tyrosine, we can say that it's a non-essential amino acid with a polar side group and is one of the 20 standard amino acids that are used by the cells to synthesize the proteins. As you can see in the picture, there are 3 systems after geometry optimization. The first one is the whole system, including amino acid, Montmorillonite, and the water. And the between, we have the periodic cell for the Montmorillonite and the water, and the third one is the amino acid. So it's important to explore the interfacial interaction between amino acid with clay mineral because it's a very important process in the environment. So the Montmorillonite, because of its high cation exchange capacity and high specific surface area, has a very large or high tendency for the adsorption of the amino acids. For the results, as you can see, I plotted density of states, which represent the number of states that are going to be occupied by the system at each level of energy for three systems: the whole system, clay water system, and the amino acid. And as you can see, the alpha band gap and the beta band gap for the whole system represents the smallest band gap. Also, from density of states, we can observe that there is a lack of beta occupation in the valence band for the whole system and the clay water system. And I think it's because of the isosurface substitution in the clay surface, and the clay surface has negatively charged, and this represents that the clay surface play an oxidizer role. Then in this model, because we have the iron in the octahedral sheet of the Montmorillonite, because of the isomorphous substitution and the iron substituted by the aluminium, and it's important to consider that the iron is one of the most important transition metals. And when we want to analyze the density of a state for the systems, the presence of the transition metals is very important to consider. As you know, the difference between the number of spin up electrons and the spin down electrons, we call it number of unpaired electrons or n up down, and the I spin specifies the spin polarization. Spin is equal to half of the number of unpaired electrons, and the multiplicity is number of unpaired electrons plus 1. In this model, I plotted density of the states for the whole model, as an up-down ranges between varies between 0 to 8, and then therefore the spin varies between 0 to 4, and the multiplicity varies between 1 to 9. As you can see in the picture, there are different density of states plot for the whole system, as the n up down or number of unpaired electrons varied between 0 to 8. And you can see the ranges between for the band gap and the energy level for the whole system. After that, in order to find whether our iron atom prefer a high spin configuration, the total energy versus the number of unpaired electrons are plotted. And we can see that there are two minima for this whole system, for n up down equal to 1 and 5. And we can see a very small difference between n up down equal to 1 and 5, and we can see that n up down equal to 1 has the global minimum. So it is the favorite spin state for the iron atom. And in the right, you can see the low spin and high spin for the crystal field diagrams. After that, I'm going to plot the adsorption spectra for the n up down equal to 1 and 5. As you can see, for the absorption spectra for the n up down equal to 1 and 5, both systems shows the absorption spectra in the near infrared region. And for the n up down equal to 1, we can see that it has higher absorption spectra rather than the n up down equal to 5. Then I'm going to plot some orbitals and its total charge density. For example, for the alpha spin up HOMO and for the alpha spin up LUMO, you can see that how the electron density focused on the atoms. For example, for the alpha spin up HOMO, you can see that the majority of electron densities are focused on the oxygens in the Montmorillonite and the water. And for the alpha spin up LUMO, you can see that the majority of electron density are focused or concentrated on the iron atom in the octahedral sheet of the Montmorillonite. After that, I'm going to plot again some orbitals and its total charge density for different orbitals for the beta down spin. Again, you can see how the charge density distributed among each atoms, for example, for HOMO-1, for HOMO orbital, for LUMO, and for LUMO +1. After that, we wanted to calculate the binding energy of the system, which means the smallest amount of energy that requires to disassemble the whole system into its individual particles. And we can see, and by using this formula, the total energy of the whole system minus total energy of the Montmorillonite plus water minus the total energy of the amino acid system, we can see that the binding energy is around minus 1.46 electron volt. I haven't found any same result for the same system. I mean, for this special type of clay and this special type of amino acid. However, for different clay and amino acid systems, I saw that the binding energy is around minus 2 electron volt. So it shows at least we have the binding energy in the same scale. After that, I'm going to show you the molecular dynamic after heating the whole system up to 1000 Kelvin. We can see that there's kind of bond breaking and bond forming in the amino acid. You can see that one hydrogen from amine group will disconnect and bond break, will break its bond and connect to carboxylic group. For the conclusion part, we can say that from the density of states plot, we can note that there is a lack of beta occupation in the valence band for the whole system, and this is because of the isomorphous substitution, and this signifies that the clay surface plays an oxidizer role. And for the different density of states, as n up down varies between 0 to 8, we can see that n up down equal to 1 is global minimum, which is preferred spin state of the iron atom. And for both spin up equal to 1 and 5, both absorption spectra are in the near infrared region, and the n up down equal to 1 shows the higher absorption spectrum. The binding energy for the whole system is equal to minus 1.46 electron volt. And at the end, the protonation of carboxylic group observed after heating and molecular dynamic up to 1000 Kelvin. Thank you for your attention. Is there any question?
Please join me in thanking Sarah.
Thank you.
And for a very nice concluding slide as well. Okay, so the presentation is open for discussion. And there are 3 questions in the chat line. Sarah, would you like to read them out loud and answer?
Okay, let me find it.
Okay, then I can read them. So,
thank you.
And you keep sharing. So, from Professor Lina, why this amino acid is used? What is its name?
The name of amino acid is tyrosine, and I think we have 5 or 6 type of group for the amino acid. So we were supposed to select or choose one type of amino acid from each group for more calculation. So there wasn't any special reason why I choose tyrosine. I just wanted to just see the interaction between this tyrosine and the Montmorillonite. I think we can say that it's randomly we choose this type of amino acid. And for the future calculation, we are going to choose more type of amino acids and then explore its interaction with the Montmorillonite.
There is question number 2. From Professor Lina, do you expect an interaction between the molecule and its replica due to the small size of your calculation cell?
I didn't get the question. You mean the size? Yeah, go ahead.
Is there an interaction between molecule and its replica in the through periodic boundary conditions? Will molecule interact to itself?
Yes, of course, because it in the three sides we have the periodic cells. Yeah, doesn't have any vacuum in the X, Y, or Z directions.
Okay, and there is a third question from Professor Lina. What is the oxidation state of iron in your system? Is it known from experiment?
I haven't checked the oxidation state for the iron. It's a good question. I appreciate it. I can double check it.
But what you were sorry, you were talking about the spin up, spin down case.
Yeah.
It means your number of electrons has to be at least even or odd. So any comments on that? Iron 2, it has 6d electrons.
Yeah.
How can you get spin up, spin down with 6 electrons?
It's a very good question. Unfortunately, I don't have background in this field.
Can you go back to the slide where you show the high spin configuration and low spin configuration? And from here, you may be able to figure it out. I think you go back a little. Go to slide number 7.
So your A panel, what do you show in the x-axis?
For this one?
Yeah, what is your x-axis?
This is the number of unpaired electrons. So the global minimum is when the number of unpaired electrons are equal to 1.
And I think 5.
Yes, 5 and 1 kind of have the same total energy, but for the n up down equal to 1, it's smaller a little bit in comparison with the 5.
But again, it looks like how many electrons you're putting on your on the panel B then.
Right, yeah.
How many electrons you have there?
5 electrons.
So if iron 2 is 6 electrons in a D level, then what iron you have in here, since it having only 5 D electrons?
When you remove one electron, how does oxidation state changes? Is it increases or decreases?
So iron 2 plus has 6 electrons. Then you take 1 electron out. What you get? What would be the charge?
And I think now the oxidation state will increase.
For how much?
How much? Maybe we should say that.
So how much you change your oxidation state?
Maybe we should say that difference between the n up down equal to 6 to 5 minus n up down equal to 5. Yes, the difference between in this two number for the total energy, it should be.
No. Oxidation state, like this concept means is it neutral or some electrons are removed? If oxidation state 2 plus means 2 electrons are removed. If you remove one more electron, what will be the oxidation state?
1? It should be 1?
No, if you add electron, it will be 1. And if you remove?
Okay, Sarah, there are 8 electrons. There are 8 electrons. Oh, is it? Sorry. I think for iron there is 2 electrons on a 4s, and there are 6 electrons on the d shell. So when you charge it with 2+, right, to get iron 2+, you're removing 2 electrons.
Yeah.
So first 2 electrons, they are gone from s orbital, and that's why you have only 6 on a d orbital. But then if you want to do iron 3+, you need to take 1 additional electron. And you can take it only from the d, because from s everything is already gone to get 2+, right? So then removing 1 electron from d, it was 6 on a d, now it's 5 on a d, you remove 1, right? So you're getting now iron 3+ instead of iron 2+. If you take even more electrons, 2 electrons off, it would be iron 4+. Yeah, you're removing electrons, your charge increasing, becoming more and more positive.
Yeah.
So just oxidation state, positive charge on the iron, right, showing how many electrons you took out from the neutral atom.
Yeah. Yeah, okay. Thank you.
More questions to Sarah?
Yeah.
Yes, please.
Yeah, sure.
Sorry, I don't want to dominate the forum, but if anyone want, have any question, please, get me out of the room. Okay, I'm glad that you dare to look at, the spin state of transition metal, because transition metal, are a different animal compared to other elements. So it's good that we had this discussion. Now, in the calculation, you can control the high spin configuration or low spin configuration by using that flat, N up down, or sometimes you don't have to do it. You can do, other way to do it. But setting the value of N up down in the in-car file is usually not enough. We still have to look at the out-car file to see if we really have the high spin configuration or not, or low spin configuration or not, by looking at the calculated local magnetic moments, right? So let's say that let's focus on the high spin configuration and low spin configuration, right? For the low spin configuration, you had that, N up down equal to 1, right? So if you look at the out-car file, what is the value of the local magnetic moment at the iron side? Do you remember that value, or have you looked at that value?
No.
It's important to check it,
Yeah.
because you just impose some constraint on the calculation. It doesn't mean that what you get out is exactly what you want to have. So it's very, very important to look at that, because even if the total magnetic moment is what you expected, the local magnetic moment can be different. Okay. So in the case of low spin configuration here, I would expect that the local magnetic moment would be somewhere, closer to 1. In the case of high spin configuration, I would expect that the value would be 4 point something. Normally it would be lower than the maximum value, Okay. So it's a good exercise to look at the outcar file and double check it.
Okay. Yeah. Okay, I will double check it. Thank you.
More questions to Sarah? I have one, I don't know, question or comment. So based on the figure that you are displaying, panel B and C, which one will provide lower minimal transition energy? Configuration B or configuration C?
I think B.
Why?
It's supposed to show that the low spin for the crystal field diagram, and
like show which electron with which spin is transferred by optical excitation.
yeah, it should be this one. This
And where does it go?
Oh, it should go to the this level, or an energy gap.
Okay. And is this transition available in the high spin configuration?
High spin configuration.
In the panel C, is the transition from T to G to EG is the same transition available or not?
No, I think.
So because of the spin conservation.
Yes,
right?
all of them are upward.
Okay, so you are telling that B should have the lower transition energy than C. Now let's go to your spectra and check if this hypothesis is correct or wrong. So which corresponds to B, which corresponds to C, and where is the transition energy is lower?
For the N up down equal to 1, I think this should be the range for the N up down equal to 1, the absorption. And for the N up down equal to 5, this picture represents that values. Am I right?
Yes. So does it agree with your hypothesis that N up down 1 has lower transition energy or longer wavelength?
Yes.
Okay.
The wavelength is around 2050, 500, and this one is around 1500
Very good.
nanometer. Yeah.
Okay. More questions to Sarah. One? More questions too? Oh, Professor Kilina, please.
Not so much to Sarah, it's more maybe to you because you probably were helping to choose. It looks like you were using iron 3 for this system. And then did you check that your total charge, it's still neutral system?
It is neutral. It is a neutral system because water serves as the pool of charges. It can add or withdraw electrons from water. Total charge is 0. It's neutral system.
I didn't get. Where do you have water? You don't have water in your calculations.
Of course, we have for the whole system. Here are the water molecules.
Okay, I got it. So you have.
Yeah, water, Montmorillonite, and amino acid.
But then, why your water is not really interacting with your molecule? Why it's not really surrounding the molecule?
And this is just snapshots from after geometry optimization. But for the molecular dynamic, you can see that there are some interaction between the amino acid and water molecule, and also the clay surface.
Right, but
so the projects were done within 3 weeks. So one cannot judge for.
Water molecules, you probably need to increase your computational cell twice. So you will really have enough water to interact with both the surface and the molecule by itself. Okay, I got it. So you're just saying that you probably have, but it does, even if you have a water molecule, right? So it looks like you charging your surface, and then you expect that this charge will be kind of getting to the surrounding. Okay.
Yeah. Thank you.
Please join me in thanking Sarah.
Thank you so much.
Thank you. And the next presenter is Omolola Eniodunmo. So Lola, would you please share your screen?
I can't share my screen.
Let me know if I need to make you co-host. Please try now.
I can.
And Lola, in some sense, continues the previous subject in the sense that she will look on optical properties of transition metals. It shows only part of your screen.
Yeah, I fixing that. Can see my screen, right? Yeah. Okay. Good morning, everyone. My name is Lola, and I'll be exploring studies on the optical spectra and conductivity of transition metal copper complex. A little background: transition metal complexes are also referred to as coordination compound complexes, which consist of a central metal atom connected to one or more ligands. transition metal complexes have high electrical and thermal conductivity, and they have a redshifting property, which is the ability for them to show up in the near infrared region. They are useful for both industrial and biological applications. However, the challenge is most of the investigated photoactive transition metal complexes are low in the Earth crust, and the TMCs which show up in the near infrared regions have been under pursuit because of limited understanding of molecular interplays. However, the goal is to synthesize new complexes from Earth abundant elements with knowledge known from transition metal complexes like iridium and platinum. How I'm going to be doing that is to rationally select the substituents on the ligands. The metal that I was using for this project is copper. It's abundant in the US and is not reported toxic or carcinogenic. So the main goal is to explore the optical conductivity properties of copper complexes. For this project, I had explored two methods. I used VAS for the DFT. Sorry, there's a mistake in this slide. The mixed basis set was for the Gaussian. So I done TDDFT and DFT for this project. Here is a view of what the complex looks like. And for the sake of DFT, the major ligand on here is the carbonitrile. Now, after carrying out vast calculation using density functional theory, I came up with this result. I checked for the energy changes in my model by exploring varying number of electrons. So what I did was I changed the different number of electrons for each of the model, and I tried to monitor what the energy changes were like. And I observed that stability was achieved when the model was reduced to 167 number of electrons. The neutral electrons contained 166 electrons. But then I realized that the energy began to surge as I increased more of the electrons. One of the other parameters I looked into was density of states, which was the spin polarized density of states for both the neutral and the anion. The anion in this case now is the one that I achieved stability for, which is the one with 167 number of electrons. Now, this is what I observed. Right here is the density of states for the neutral, and here is that for the anion. When I checked the band gap in the alpha region, I got a band gap of 1 electron volt. For the anion, I got something lesser, about 0.25 electron volts. But when I checked for the band gap in the beta position, it was around the same value, which was 0.25. So I was able to conclude from this that the anion state will be a better conductor, although the neutral state isn't so bad because it falls between the range of the band gap expected for a conductor, which is about 1 to 3 electron volts. One other parameter that I also explored is the quotient orbital because I wanted to look at the metal to ligand interaction. Now, this is what I observed. For the neutral model, which contains 166 electrons, there was a significant metal to ligand transfer. And I was able to conclude that there is quite a level of coordination between the central metal ion and the ligands, which is great for optical activity. However, for the stable anion, I observed a ligand to ligand charge transfer. The other parameter that I also explored was absorption spectra. Now, this is what I noticed on checking for the spectra. The anion, which is the one which I considered stable with the 167 electron, it showed up in the MIR region, which is the mid-infrared region, with a wavelength of about 3,800 nanometers and a reasonable level of intensity. But the neutral state showed up at about 5,200 nanometers, but with a higher intensity. And I was able to conclude that the neutral state of this model will emit light the brightest compared to the neutral state. Now, remember that the main ligand that I used for this DFT was the carbon nitrile. However, for the TDDFT, this was what I did. I sort of like changed the subsequence on the model. I explored for the carbon nitrile, hydrogen, NO2, NPH2, and OCH3. And this is what I observed. The carbon nitrile, NO2, and the OCH3, they exhibited brighter states in the NIR region, and the carbon nitrile showed up with the highest intensity, which sort of like agreed with the result from the DFT. Now, for my conclusion, the spin polarized spectrum of the neutral state emitted more light in the MIR region compared to the anion. With the TDDFT model, this subsequent CN, OCH3, and NO2, they emitted light with about reasonable intensities in the NIR region, even though the subsequent with the NPH2 and hydrogen showed up with slightly higher intensities. So I'm able to conclude that my copper complex will perform better in the neutral state, although it might be more expensive because it has like a higher wavelength compared to the anion state. Yeah, but I mean, at the end of the day, I concluded that it will be a better material for emitting in the NIR region. Thank you.
Please join me in thanking Lola. And the presentation is open for discussion. So there is a first question in the chat line from Professor Svetlana Kilina, checking what is the charge of copper, which charge of copper corresponds to the total number of 167 electrons.
It's a 2+. So what I went on to do was to explore copper 3+. And this was what, yeah. What I'd gone ahead to do was to explore for the copper 3+, which is 168 electrons.
No. If your 167 is 2+,
yeah,
then removing one more 166 will be 3+, and adding one more 168 will be 1+, right?
Yes, sorry.
Okay. Did Lola answered her question?
Yes.
Okay.
What is the charge state of copper in the neutral complex? At 1+ or 2+?
2+.
So let me repeat the question. You answered in previous question that 167 is 2+. What is the charge of copper in 166?
Yes, in 166 it's 3+.
Is that 3+ stable? Do we know that copper 3+ stable in some complexes?
Can you return back to your file to your picture with energies? Yeah, this one. So where would be your 3+?
Right here. It's somewhere close to, yeah, right here. This is where the 3+ is.
So the difference in energy is within thermal fluctuation. So it seems possible to exist, to thermally populate.
And Lola, can you go to your DOS once, which you were showing with spin up, spin down?
Right here?
Yeah. So technically your DOS is not homoluma, right? So this is for, so your 66, this is neutral. So again, this is copper 3 and 67,
Yeah.
67 then would be copper 2 plus.
Right.
And this is the most stable structure. I mean, stable in terms of the energy.
Yes.
It looks like copper 2 and copper 1 are approximately of the equal energy.
Yes. If I go back to it's somewhat close to each other.
But we're looking on a copper 2, right? For the
yes.
So in this case, I think your homoluma, I'm a little bit confused with your spin down states, right? Because technically it looks like the lowest, what would be then, what would be your down state? What the gap if you really consider the different spin states? If you're not taking the gap between the same spin, but if you take the actual smallest energy independent on a spin, what would be then this gap?
Are you talking? Sorry, I didn't exactly get your question. Are you talking about in the beta position? I'm not sure what you're saying.
For the beta, you're showing alpha and beta, right? For what is on the top is your spin up, what is on the bottom is down, right? So my understanding that technically for your first case, 166 electrons, the actual gap is not coming from alpha and alpha states. It's coming from alpha, HOMA, what you define, red, field red, and then it should be taken unoccupied magenta line, which means you will have no gap in this complex at all. It's completely closing, right? Because technically, because in this complex, if spin orbit coupling is drawn, then you can allow the transition with flipping the spin. And then you really have a transition from state, occupied state with spin up to the unoccupied state with spin down, which has energy around -4, with both having the energy around -4. So your gap will be negligible. So you really don't have any gap in this complex.
Yeah, looks like it. Yeah.
And also the same would be true for your copper 2, but for copper 2 in this case, you need to take it looks like you need to take in this case, I think it looks like they're pretty much the same energy up and down. Unoccupied levels are the same energy, or at least at this resolution, hard to say. But you need to take the gap between beta state occupied, right? Because your energy occupied beta state is now providing this highest occupied state corresponds to the spin down.
Right, right. Luma alpha minus HOMO beta.
Or maybe also Luma beta, because it's really hard to say.
No. In VASP, they always populate alpha with more spins than beta. It's just a convention.
Okay, yeah. So when you calculate your spectra, you calculate in spectra independent on a spin, or you calculate the spectra only based on the spin up, spin like when you calculate the spectra, what exactly you which states are you taking into account in your calculation of the spectra?
Let me help. Answer is second option, spin is conserved.
Okay. But spin orbit couplings are included in these calculations or not?
Not here.
I see.
More questions to Lola?
Can I one
yes,
more?
Please. Yes, please.
I want to go back to the basis of the calculations. So you say that for a certain number of valence electron, you have like copper 2+. So some other number you have copper 3+. How do you know it is copper 2+ or copper 3+? How do you know?
Are you talking about this slide? Sorry.
I mean, in general, like let's say that you do a calculation. Let's say for the total number of electrons equal to 167, and you said that you had a copper 3+, right?
Mm-hmm.
How do you know it's copper 3+?
That's a good question because I wasn't exactly sure of which one.
Yeah, that's important, right? I mean, we may assume that it's copper 3+, but
Yeah.
in reality, it may not be, what we expect. So you still have to check the output, the output of the calculation to confirm that.
It's not really true because you're not expecting that oxygen will be positively charged, right? You're not expecting that DFT will result on the nitrogens being positively charged.
Well, would you please show the molecule itself a few slides before?
So you can easily, the only possible positive charge can be either on carbons and copper. But there is no question, if you're comparing copper and carbons, then for sure copper will be more positive comparing to the carbon, right? So there's really no such a big ambiguity in this case where exactly the positive charge will go, right? So you can estimate the total number of electrons based on the valence number of electrons for carbons, nitrogens, oxygens, right? Copper, taking copper 1, right? For example, you know how many electrons should be on a copper 1, so it's like 10 electrons. And so you know the total charge, you know the total number of valence electrons in a system, right? And then you can just, if you have neutral molecule, it means because the ligands, these two oxygens on the bottom, right? So they actually losing the hydrogen and they becoming negatively charged. So total the charge on the ligand is -3. And because to have this molecule neutral, the only way to have it neutral, the attachment group on the R is neutral as well. So the ligand is -3. So then to have it neutral, there is no any way rather than kappa being +3. If you make this to be -1, then kappa would be +2. If you make it -2, then kappa will be +1.
So that is true, and it may be clear in this case. But still, we still need some confirmation from the calculation, right?
Right.
But it's very easy to go into the archive file, look at the calculated local magnetic moment, or you can, plot the charge density. You take the difference and see that, the extra electron or extra hole is going to be localized on copper.
It is much harder to calculate it in a VASP for this system, right? But it's much easier to get this information from the local basis set calculations with Gaussian. And I think Lola was checking these charges in Gaussian for seeing the difference in the charge on the copper between this kind of when she varies the charge on the entire molecule. Yeah, it's a good question. So when you talk about what is the charge, probably it's a good idea to confirm your results with some computational data.
Right.
Thank you for the discussion. More questions to Lola? Let me ask, just for curiosity, would you please show if do you have results for 168, like density of states and spectra for copper 1+, and do they show anything drastically different?
Yeah. So for like the density of states, looks like it's a singlet. Which I mean, singlets are more stable. So yeah.
Okay.
Yeah.
And it also has near infrared transition. Okay.
Yeah.
So,
yes, it does.
More questions 1, more questions 2, more questions 3. Let's thank all once again, and you can stop sharing. So now there is a last in order, but not least in importance. Steven Westra, would you please share screen and let me know if okay, you have it. So Steven was extremely brave to take a subject which is basically undoable. It combines challenges of the first talk of the two-dimensional structures, and it combines the challenges of everyone who did transition metals. So he is working on two-dimensional materials with several transition metals with interacting spins. And even small steps in this direction could be very interesting. So, Stephen, floor is yours. And make sure your microphone is unmuted.
Yes, I was looking for the control for that. And so, as you can see from the title, my project was on computational modeling of a plausibly potential Kitaev quantum spin liquid superconductor known as Alpha-Ruthenium chloride. And there should be a 3 on the end here, but that's not important. So the introduction. So obviously superconductors have a large variety of uses in many fields. In particular, computers could benefit from lowered resistances. And energy transportation and storage of all kinds would benefit greatly from stable superconductors. But one thing that has continually troubled the development is that all existing superconductors require the use of very exotic transition metals, complex alloy structures, or extremely cold cryogenic conditions, which are obviously very impractical for everyday use. A relatively new type of superconductor that has the possibility to overcome a number of these issues is known as a Kitaev quantum spin liquid. Just to continue. So a Kitaev quantum spin liquid is a phase of matter that is theorized to exist in two-dimensional magnetic structures, and it's particularly pronounced in those that have a hexagonal or honeycomb crystal structure similar to what you would see with graphene. Alpha-Ruthenium chloride is of particular interest in this, in that it strongly exhibits many traits that were thought to be indicative of this type of phase of matter, and it is relatively trivial to produce. It also individually exhibits many unusual properties that have yet to be fully explained in published literature. Another model. So from the top left to the top right, we have just a basic repeated unit cell showing the roughly hexagonal nature of the alpha-ruthenium chloride. Next to that is a spin density diagram, which shows that we do indeed see that our free spins are concentrated on our ruthenium atoms and are with our total charge being evenly distributed across the unit cell. And we have our density of states for two different spin conformations. Left is the antiferromagnetic, where we have all paired spins, one up, one down. And the right is the ferromagnetic unpaired spins, where we have two up. It's not entirely obvious from looking at that, but it is found that the antiferromagnetic is the more stable of the two, with a slightly lower total energy. And so the models that I worked with, were computed using a collinear spin polarized DFT, which differs from original Kohn-Sham equations by using a series of Pauli matrices to find the densities, which are shown in the lower left. An important point of the collinear nature is that it only takes the real portions of the spin density and ignores off-diagonal interactions, shown with the blue circles as the real portions. And what this does is it allows us to find electron densities in terms of X, Y, and Z when they are otherwise identical. And this differs from the original one, as I said, is that it's a summation of matrices rather than just a total summation of the absolute value of the pi rho I r squared. There we go. Method. So alpha-ruthenium chloride is a two-dimensional material by nature. It is a similar in structure in bulk form to graphite, or graphite, a van der Waals force layered material with thin single atom thick layers. And as such, it can be well estimated by the Ising model of a magnet, which uses the following Hamiltonian equation. The particular component of importance is the J sub ij, which is accounts for the interaction between neighboring spins and is a material constant. And all of the following calculations and geometries were calculated using VASP software. So several calculations were run to find the energy of the unit cell at several temperatures and test to see if there was any change in magnetization. The temperatures chosen were 300 Kelvin, 200 Kelvin, 100 Kelvin, 77 Kelvin, 8 Kelvin, and 4 Kelvin. The reason for those choices is they are well-defined points for room temperature, the temperature of dry ice, solid carbon dioxide, the transition between what is considered high temperature and cryogenic temperatures at 100 Kelvin, 77 Kelvin for the boiling point of liquid nitrogen. 8 Kelvin is a point that's a particular interest to ruthenium chloride due to some unusual behavior that it demonstrates there for its heat capacity. And 4 Kelvin is liquid helium. Yeah, and as I said earlier, the calculations were done for both the ferromagnetic and antiferromagnetic spin conformations. So from this, since we are only considering the collinear directly in or out of the magnetic field, we can take our energies as being plus or minus mu h, with h being the external magnetic field, and we can calculate our magnetic moment as n tan h of our energy over the Boltzmann constant temperature, which would be equal to our internal energy over the strength of the magnetic field. From determining that, we can also find our specific heat from the first law of thermodynamics. Results. So the VASP calculations showed no change in magnetization with change in temperature, and a overall decrease in unit energy with decreasing temperature. The bump that you will see on the graph on the right here is the calculation for liquid nitrogen. And from this, we found that the value we were getting for J was 0.6 electron volts, which I will discuss further later. So performing the calculations described earlier gave us the graph on the left for our specific heat versus temperature. And on the right, we have a published graph showing a comparison of existing computational models of alpha-ruthenium chloride and experimentally collected data of its heat capacity. And as I said at the bottom. So one thing that we notice from this is that these are rather highly improbable results. We are not really very close at all to seeing a good match with existing data, and there are a few theories that I have as to why, and which I will get to in the next slide. It is likely that the small size of the unit cell, since we are only working with 2 ruthenium atoms to speed the calculations along, likely caused an overestimation of the interaction constant between the spins, and that this is throwing off everything. Other work that was performed using a less computationally rigorous method gave much more reasonable figures when using much smaller values for J. And future work on this would be to redo calculations and correct for this overestimation to hopefully get a better fit for data.
Okay, please join me in thanking Stephen. We can be interrupted because Zoom meeting was set up for 2 hours. So let's thank both Stephen and all presenters. But in case we didn't get interrupted, we can go to the question section. But do not be surprised if by some reason something happened. So we made everything in time. So there is a question from Professor Han Huang. It should be alpha-ruthenium chloride, isn't it? I don't think alpha-ruthenium chloride is stable.
Yes, it's alpha-ruthenium chloride 3. I'll back up a bit. Yeah, we have in total 2 ruthenium atoms and 6 chlorine atoms in our unit cell. The reason it's missing a subscript is just a formatting issue with writing this.
Okay. Next question from Professor Han Huang. Is ruthenium 3 plus in high spin or low spin configuration?
Should be low spin.
I would agree. So how many unpaired spins on one ruthenium?
There are 1.
Okay. And on behalf of Professor Han Huang, I would ask, did you try for MEG, for magnetization value in the Aussie car? Does it show for ferromagnetic 2, which would be 2 spins, or okay? So it is confirmed. More questions to Stephen? Yep, please.
Stephen, can you go to this comparison between your data and some experimental data, right?
Which has both have peak at 100 Kelvin, right?
I'm a little bit confused. So this is the data. This was already from some paper, right?
Yes.
And which would be good idea actually to cite the paper on your, since you're showing the data from someone else. It would be a good idea to really refer to the article which you are taking this data. But there's also the red line corresponds to the modified ab initio model. Can you give a little bit more ideas about how, and it looks like you said, oh, our data are really not so good, but I think they correspond in 100 Kelvin. Well, if your scale is in Kelvins, right? Yes. Your temperature is in Kelvins, I hope, not Celsius. So your 100 peak is kind of increasing, and they have the peak on 100, and then it's going down, which also follow in your predictions. I think the only disagreement is in a very low range of temperatures around less than 10, right? Which looks like logarithmic scales. I don't know exactly what is the temperature where they have this peak. And in your case, looks like you really have 0 instead of a peak there, right?
Yes.
So it's really disagreement in this very low temperature range. Can you give a little bit more ideas what exactly is different from your, and I think it's really difference in approach, which provides this difference in this low energy disagreement. What exactly?
Negative.
Yeah, what exactly different in their approach, ab initio approach, compared to yours?
I don't recall it exactly from the paper. It's been a while since I've read it, but I think the issue with that would be is that I used a collinear method and they used a non-collinear method. Since
what does it mean? Please explain.
One of the leading theories of what causes that large spike you see at about 8 Kelvin on the experimental data is that there is an interaction that arises from the off-diagonal components of the electron density, and that by using a collinear method, we ignore that and treat it as non-existent. And so that would obviously dramatically impact the results.
And why it's not so important for 100 Kelvins for the high temperature regime?
Oh, because that effect disappears at high temperatures experimentally, which is why it drops precariously in the experimental.
But it's still present at 100 Kelvins. But your theory provides this peak at 100 Kelvins, but doesn't provide in low temperatures, right? So like these collinear, non-collinear calculations looks like they probably not so important when you go to 100 Kelvins. Any idea why? Honestly, I don't know the answer. I mean, I have a few ideas, but
if I had to speculate on why, it'd be that well, obviously, as we get in higher temperatures, we have higher energies in our unit cell, and the effects that are leading to this deviation we see are less prominent, simply because they don't scale at the same level. They, as the temperature gets higher, the ability for the spins to flip against the magnetic field increases, the probability increases, and the overestimation of our interaction becomes less important.
Okay.
So, Stephen, what you've told about spin flip, spin degrees of freedom contribution to heat capacity corresponds to the peak at 8 Kelvin. But what is the nature, which degrees of freedom contributes to the peak at 100 Kelvin? So in your modeling, you run molecular dynamics, which means you enable motion of nuclei, right? Nuclear degrees of freedom or oscillations of nuclei around. Does it have any relation to the second peak?
It could. Unfortunately, I was not able to get the program for making a video out of the molecular dynamics calculations to work. So I wasn't really able to look on that, but
you can hypothesize that likely the second peak originates from activating some interatomic vibrations. So it would fit the Einstein or Debye models for heat capacity.
Yes.
So it's not magnetic nature; it's just oscillations in solids. Okay, more questions to Stephen? More questions one? More questions two? More questions three? So let's thank Stephen once again. You can stop sharing, and Stephen, yes. So let me thank all visitors for very active discussion and even if not asking questions, for support and attending this meeting. I think it was very inspired and enthusiastic discussions of several scientific issues. Thank you, attendees of the class, for investing time not only in academic learning but into these projects. Hope you will take it as a baggage to your research life, and you will see soon the grades in campus connection systems that I hope you will not regret. Okay, so if there are any brief comments or suggestions, please speak. If no, let's announce the course of 2021. Oh, time goes so fast. Finished and completed successfully. Thanks everyone, and you're welcome to disconnect, and I'll stay connected just in case there will be more informal discussions. So, thank you.
Thanks everyone.
Thank you.
Thank you, Dr. Killen, for a great year.
Oh, thank you. Thank you.
Thank you, Professor.
Thank you, Keya.
And thank you, Professor Lina. Bye.
Thank you, Dr. Killen. Thank you, Dr. Lina, everybody, especially for this wonderful semester. Thank you, Dr. Killen. We really appreciate your support and help and teaching us. I wish you the best and have a nice week, weekend, year, month. Take care.
Thank you, sir. And what's the name of your cat? Can you please repeat? I've forgotten.
Sorry, this is my cat.
What's the name?
The name is her name is Malus. Yes, Malus in Persian means very cute.
Oh, okay. Okay.
Thank
Thank you. Thank you, Sarah.
And I just want to say hi to London. He's previous students from Dimitri's class, right? So I don't know, didn't see him for how many? Was it 2 years ago, right? When you took this class?
Hello. I don't know if you can hear me very well or not.
We hear you and very happy to see you.
Did you take Dimitri class 2 years ago or last year?
Was really
It would have been 2 years ago.
2 years ago. Okay, great. How are you doing? Are you good?
Yeah, pretty well. I have my own apartment now, so